This slide shows you the energy why we do consumed by the devices. The slides shows you the energy which we are consuming while doing various operations through our networks component. First one is wireless data. Just by transferring a data, a single bit, how much of energy we are consuming? Almost 10 to 30 microjoules, although it's very less. We are not transferring only a single bit. We are transferring tens of bits altogether. You can assume how much of energy we are consuming when we are transferring the data all across these data. Similarly, if you just access the internet, you just open your Gmail account, much of energy per bit. That is 40 to 80 nanojoules. Again, it's very less. Think about the situation, and the billions of the users are all together working onto the internet. So how much of energy they are using? All these, the first 5 or 6 operations are based on the communication link. 4 or 5 operations we do at the logic level. So everywhere we are consuming the energy, and our aim is to reduce this energy consumption. And that is why we are planning to go for the photonic devices as well. Although, as on today, the photonic devices are consuming more energy as compared to the electronics. But nevertheless, in coming time, we'll be coming up with the products, photonic products, which will be consuming the less energy. I'll cover some of the milestones which we have achieved through the optical communications. Way back in 19, these are what discovered, and thereafter we started thinking whether we can for our information. Mid of 60s, invented the guided wave optics, which was demonstrated into the lab, and it very successfully transmitted the information. By 1970, we started producing the low loss fibers were applicable for our telecommunication application. Indeed, 1977, the first fiber cable was laid down somewhere in the Chicago, US, whereby we started using the low loss fibers for the application of telecommunication engineering. Every year, we invented the semiconductor. Between 17 and 80s, we started use of fibers in telephone. Earlier, the networks were known as SONET, synchronous optical network. In mid of 80s, we started with the LANs, WANs, and MENS. I'm sure all of you are aware of this. Area network, wide area networks. We are using fibers to communicate our information. 1988, first transatlantic cable was laid down, all across the, which was used to connect the European continent. And even as on today, there are 2 cables which are connecting these 2 continents. Of our internet data, indeed, more than 80% of internet data is actually passing through these cables only. We invented EDFA, erbium doped fiber amplifier. Like every network requires regain the strength of the signals. We also invented EDFA, erbium doped fiber amplifier, to use it with the optical communication link. 90s, started working with the DWDM, dense wavelength division multiplexing. Electronics engineer, you might be aware of PDM, FD, time domain. Similarly, we started with the using dense wavelength division multiplexing, optical communication. In late 90s, the people started coming up with the intelligent optical networks, which can actually compatible with the available electronic devices, so that we can increase our and the communication networks. And that's why we had got these generation 1G, 2G, 3G, 4G, 5G, 6G, and onwards, people have started coming up with the all optical devices, which we call in short O devices, where I can have the input in optical domain, can process them in optical domain, and I can get the output in optical. Earlier, we were having OEO because it was coming into the optical domain, but we were having the processor which were working in the electronic domain only. In that case, we would require conversion from optical to electronic and then electronic to optical. Just to avoid these to conversion and to match the speed of input, output, and the processing unit, we started working with the all optical devices, that is triple O devices. 2010 onwards, this beautiful word came into the picture, that is PICs, photonic integrated circuits. Like 2010, we invented various devices which were working in the photonic domain. Started thinking, why not we come up with a chip which will have all the photonic components all together, and if we can integrate them, work together, that we can actually replace some of the electronic chips by the photonic chips. Now the people are coming up with a lot of photonic chips, which we have already started using, especially in the cloud computing centers and data centers. For the high performance computing, we are using various photonic chips as well. This picture is very interesting. The first, you can imagine about this picture, this is a BTS site. Being a user, we all want that our cell should get signal strength. So there is a tremendous pressure on the network service provider, because they are not going to change all their equipment within a month or within a year. It needs a decade to change their network. Every day we are kept on increasing our application, as well as the number of users are adding into the market. Because of that, our signal strength is going low. Wants a good signal. Second one is bald person. Various reasons for losing the hairs. Doctor says sometimes you may lose your hairs if you are bothering for your data loss, which is because of the network. If your signal is not good enough, if you're not getting good signal, if you're not able to talk properly on your cell phone, you get tension. Just because of that, even you may lose your hairs also. So that is another problem this communication networks are posing for us. Third is, everybody is in a party, but nobody is talking to each other. Everybody is working on the mobile phone. Very common. Few of you are still now you are working with this. It's the problem with the network service provider. Because the people want their data every time on their cell phone, and this much of pressure the network service providers are facing. It's very easy to use them. The services are not good. The BSNL is not good. The Reliance is not good. They're not thinking about how much pressure we are actually posing onto them because our habit. Graph talks about the use of VLSI to reduce the energy consumption. Here you can see black dots. These black dots are showing because invention of VLSI, that is very large scale integrated circuits. In short, the miniaturized electronic chips are able to reduce the energy consumption. But even then, the consumed by the internet services are kept on increasing. This was the done by a few researchers from Japan, and they published this paper a conference. They come up this data only for their country, which says despite of having great invention of various devices through VLSI technology, whereby we can actually reduce the energy consumption. The energy used by the internet applications are kept on increasing. And the main reason is the user and their demand for various applications. Still, we are consuming a lot of energy. You just think about this situation that somewhere around 8 to 10% of energy generated for all the applications we are consuming for our internet and telecom purposes only. What could be the solution? The fastest solution could be if we can come up with the PICs, that is photonic integrated circuit. If we can come up with chips which will have the photonic devices all together to work together, and if we can replace the electronic chip, and again the energy will be another constraint, which is still today with the photonic chips. We are still working on to reduce the energy consumption by the photonic chips. But if we are able to come up with the photonic integrated circuits, we can have 3 or 4 specialized applications. One is will have a high bandwidth because the optical spectrum is used. So high bandwidth means many more applications can be added into the network. High speed, the data can be transferred at the speed of the light. In that case, you'll get everything very quickly on your cell phone. Immune to noise and EMI. If we are avoiding the electronic or the electrical circuits, that means we are more immune to the noise and more immune to the electromagnetic interference, which are actually not applicable for photonic devices. More secure, it is very difficult to tap the information from photonic circuits. It's very easy these days to tap the information from your electronic devices. But if you're coming up with the photonic devices, information would be more secure. Cost effective, as on today, the cost of the photonic devices as compared to their counterpart electronic devices, the cost is too high. But if we are able to produce them in bulk, then the cost will also be a bit less. So ultimately, this technology will prove as a cost-effective technology as counterpart for their electronic devices. So with this, up to this much of 3 slides, what do we understand? What are the important factors for telecom network service provider or internet service providers? What are the different pressures they are facing? These 3 headlines I got from a Cisco white paper. They released this paper in way back in 2017, 8 years back. So maybe the data is even more. There is an extreme increase in network traffic because of the number of users adding into the network. Earlier, we were having only one cell phone in the family, but now everybody is having a cell phone. So the number of users are increasing like anything, almost 30% per year. While they are having the same networks for almost a decade. Only after a decade, there is a possibility that they will come up with new equipments. They will be putting up some other BTS sites. So while every year we are kept on increasing our users, number of users. Second is increased requirement of cost. This will also pose a problem with the network service provider. To handle this much of traffic, they need to come up with the new infrastructures, new BTS sites, new equipments, and for that they require huge money to invest. While being a user, I don't want to increase my telephone bill or my internet bill, but expect from the on the other hand, I do expect from the other hand, from the service provider that they will provide me the better services by putting a lot of money into the infrastructure. Third is ecological and economic issues. So these economic issues are for both of us, for the user as well as the network service provider. The moment they will add few more services, you will always get that your cell phone is now old and you'll have to replace with the new one because new services are being added into this. So these economics are not only for the network service providers, but this economics problems or issues are related with the users also. Ecologicals. These days you might be hearing about the hazardous problems posed by the 5G or 6G network. So we are a little worried for our health also. We are not at all bothered for the animals or the birds, which are already been affected in huge amount because of these network services. What could be the alternate solutions? We can plan to come up with the new photonic chips, new photonic ICs by placing a small photonic component onto it and to work them all together and to get the data at a better speed so that we can do the operation at a bit faster rate. We are able to do this. These will be the important benefit which will be out of our efforts if we go for the PICs. We get the high speed and high bandwidth, high capacity signal processing in optical networks. We'll have a function, most of the function will be immune to noise, more secure and cost effective at large. If you happen to be in your lab, you might have seen that all the computers, they are placed on LAN. They are connecting with each other with the optical fibers. If you go all around your campus, you will see all the computers are connected again with the optical fibers, which basically a part of MAN. Then we have a WAN also, wide area network, where we can connect the computers lying in various cities. Similarly, we can connect the computers through the optical fibers, which are lying all across the continents also. So we are having the fibers which are going through the seabads, and we are connecting all the electronic gadgets through our optical fibers only. So this much of applications, we are already having optical fiber. Now the question is, how do we can use the optical fiber or optical waveguides to connect the small photonic components onto a chip? Because if you happen to be in a cloud computing center or data center, you'll see most of the racks are having various electronic and photonic components, and they are connected with the optical fibers. But within the chips, you'll see the interconnecting patterns are based on copper wires only. Now, because of this, there is a speed mismatch, because when we are working with the optical fiber or the photonic components, our data is transferred at the speed of the light, while in the electronics, the speed is bit low. So what the problem is, still we are using the electronic chips which are having copper connects, and because of that there is a speed mismatch. And to overcome these speed mismatch, we need to replace these copper wire by our optical waveguides. So this is also another problem facing by the photonic researchers, to come across with the chips which will have the optical waveguides connecting all the photonic component all together, so that we can avoid this speed mismatch problem. Why optical interconnects for short distance are required? If you see on this graph, you will see this graph is showing the power dissipation with respect to the interconnection length. If we are using the copper wire, the power is bit less. But if we are using the optical waveguides or photonic wire, the power remains constant, whether the distance is 10 micrometer or it is the 10 millimeter or 100 millimeters. So ultimately, for a very small distance, still the power consumed or power dissipation by the copper wire are less, and that is why the copper wire is still used with the electronic chips. And we actually need to work upon this so that we can reduce the power dissipation for the photonic interconnects as well. If we differentiate the integrated electronics and integrated photonics, what is the difference? Way back in 1947, we invented the transistors, which you might have studied NPN and PNP. So these transistors we invented somewhere in 47, and with the span of 7-8 years, we were able to come up with first EIC, that is electronic ICs. Because the growth was very good in electronic IC industry at that time, many players were investing money for the electronic ICs, and we were able to got the first electronic ICs within the span of 7 or 8 years after inventing the transistors in 1947. While we got the first optical ICs way back in 1969, and that was for the some lab applications, not for the commercial application. And now today in 2024, we are talking about the integrated photonics, because we have not come across that much of growth what the electronic ICs have seen in last couple of decades. So there is an exponential growth for EIC industry, which is actually not for the PIC industry. Operational and fabrication differences are there, because photonics more or less depends upon the material. And the problem with this, when we wanted to come up with the photonic devices, there are many issues related with the materials. We need to come up with the devices which are actually built on different material, not only on a single material. Like for an example, if I'm using a silicon base, I cannot come across with the sources or detector. I can come up with many more devices, but for sources and detection, I would need a different material. So these are actually posing a problem. PICs are equivalent to EICs. Operation more or less are same. Whatever the EICs are producing the results, the same the PICs can also produce. The important similarity between the EICs and PICs are related with the Moore's law. Moore's law is very important for electronic engineers. Moore's was a scientist. He predicted that the speed by which we are placing the component onto a wafer or onto a substrate will be able to make them double every year. Initially, he predicted that every year we'll be able to make our IC more compact, because we'll be able to produce or place more components with the speed of almost double every year. But after 10 years, he revised his postulates, and he says, no, we would require at least 2 years, right? So at least 2 years to make our components doubled onto a substrate. And I guess on latest I read somewhere in in a blog or in an article. Now this even not the 2 years, somewhere around 2.3 years. So 2 years, 3 months we require to make our components double onto the wafers. So this shows the graph with what speed the number of components can be placed onto the wafer. So the bigger line is for the EICs, and you can see we were by 2010 we were able to place almost billions of transistors onto a single substrate. Now the good thing is the same slope we are having for the photonics also. Although we are able to only place 1,000 components onto the substrate if we are coming up with the PICs. But the good thing is they are also following the Moore's law. Probably will also be making the numbers double every 2 years or a little higher. Not only the researchers or the scientists are working towards the photonics, many big companies or big giants are already on into this market, and they are trying to come up with to cope up with the electronics and the photonics altogether. They are trying to come up with the electro-optics devices or pure photonic devices. You can see the many more companies are working onto it. Cobra, Philips, Siemens, HHI, Alcatel, NTT. So many big companies are also working onto it. If you being an electronic engineer, if you want to pursue your higher study in photonics, or if you want to make your specialization optics or photonics as an specialization, you'll have ample opportunities to place yourself with the big companies as well. Initially, there was a slow progress in the development of PICs. As I said, we were able to come up with the electronic ICs within the gap of 7 or 8 years after inventing the transistors, while even 2024, we are still talking about the integrated photonics because we have not come up with the devices which will replace all the electronics chips. So there was an initially slow development for PICs due to the fabrication, economic and complexity related issues. Major players were not ready to invest money for the photonic industries because at the time the electronic industries were already matured enough and many more products were coming. But now most of the industries are putting efforts and investing a lot of money to come up with the photonic devices as well. But after inventing the semiconductor-based LEDs and LDs, there was a good speed to come up with the photonic devices. And now we have the devices for communication systems for data storage, processing, and sensing as well. Many functional devices are already available in the commercial market. You can easily find them for amplification application, for attenuation, for multiplexing, demultiplexing, modulation, demodulations, switches, couplers, detectors. All the photonic components are already available, and they are available commercially as well. Major breakthrough when we invented the SOA, that is semiconductor optical amplifier, and these are the very miniaturized amplifiers which can be placed onto a chip also. Earlier we were using a big size amplifier, EDFA based amplifier, but after inventing the SOAs, the concept of PICs was easy for everyone. Still, the missing factor is lack of standard fabrication facilities and packaging technology. As even today, most of the photonic chips are being produced in with the help of the available electronic fabrication technology only, because we need a different kind of fabrication setup. We would need a lot of investment from the big industries to come up with the fabrication facilities and also for the packaging technology. Why the PICs are becoming popular? Because they've been proven to be the robust, compact, and flexible. We can place more and more component onto a single dias. We can make them more flexible in terms of the operations. Integration of several components can make these devices more faster. They have shown the reliable and satisfactory performance as on today. They have also energy efficient. They are able to produce energy efficient network systems. So we can expect, if not all the photonics, but we can expect that there will be a shift from electronic to electro-optic devices. Like most of the networks, telecom networks are already having many more photonic component into the picture. But in the coming time, all the electronic gadgets will also have the photonic components. If not all the electronics is being replaced, many components would be in photonics working in the photonic domain only. So there are various integrated photonic technologies which we are working on to it, using the planar light wave circuits or integrated optoelectronic devices whereby we are placing the electronic devices as well as the photonic devices, and they are working all together. Then wafer scale technology on substrate, we can come up with the various chips also. There are some technological limitations as well. Like we have the technology limitation for the electronics. Similarly, we have some technology limitations for the photonics as well. So this graph shows history and evolution of monolithic INP-based PICs. Initially, the important material which was used to produce photonic devices or the photonic chips was indium phosphides. We started way back in 1970. Initially, the people came up with some research articles or some blogs or some theories that how comes the indium phosphide can be used to build photonic devices. And thereafter, you can see from 1970 to 1985, there was not much progress in this direction. But after 1985 to 2010, we have come across many devices which are based on INP photonics. What are the important photonic integrated circuit technologies which are available or the people are working as on today? The silicon photonics, the silica on silicon, where we are using the fused silica, the components of third, fifth integration platform, and we also started working with polymers to come up with the photonic devices. If we see the PIC development approaches, which are mainly divided into two categories, one is silicon-based photonics, and the other one is the photonic based on the third group of elements. Silicon, why do we use the silicon? Because it's easily available, versatile in nature, low cost material, and the best thing is it is compatible with the available electronic industry fabrication facilities. Because whatever the electronic industry fabrication facilities are available, they are compatible. If we are working with the silicon photonics, we can use them. Most of the equipments, we can use them to fabricate our chips. However, why do we use the components of third, fifth group of elements semiconductor? Because we wanted to have the high power and high frequency application and high light emission efficiency. Because of their high light emission efficiency, we are able to bring the lasers onto the chips. Why silicon photonics is becoming popular these days? Because as I said earlier, we started with the INP, that is indium phosphide. But after 2005, people started working with the silicon as well because of the compatibility with the electronic fabrication facilities. The track record of success is very good. Silicon is already very popular in electronics. It is compatible with the EIC fabrication technology. We can use the same technology to build our photonic chips as well. They have proven to be the good in performance, yields, robust, and importantly, they are reproducible. Production of PICs in high volumes is also possible if we are using the silicon photonics. And more importantly, as far as the application part is concerned, they are more transparent for the telecom windows. So we can actually produce silicon photonic based chips which are applicable for photonic telecom networks. If we are able to come up with the silicon photonic chips, we can use them for data centers. We can use for optical telecommunication purpose and for our networks as well. There is a bit challenge with the silicon photonics because since it is an indirect band gap material, so it is very difficult to how to bring the light onto the our chip and how to bring back the light out of it. Because how to build the source and how to build detectors onto the silicon. And that is why we need hybrid kind of solutions where we can use the silicon as well as some other material, which will be providing the light onto the chip and which will be taking back the light from the chip. So towards silicon laser, there are some approaches like we can use the hybrid silicon PICs technology. We can use some other material with the silicon and have some kind of hybrid arrangement whereby we'll be able to place the laser on chip, some bonding of third fifth group epitaxial layers, heteroepitaxial growth of third fifth group on silicon. Similarly, we can grow the germanium on silicon platform with a selective growth. And there are various elements of third fifth group of elements from which are semiconductor in nature, and we can use them to build their PICs. And why we are using them, the advantage would be if we are coming up with this, will be they will be providing solutions for the lasers, optical amplifiers, modulators, and detectors. So if we are using other material other than the silicons, it will be easy for us to produce laser onto the chips and detection devices onto the chip. Monolithic integration is possible. Passive and active components within the fully functional chips can also be possible if we are using the elements from the third group of tables. However, there are some disadvantages because we would require extensive integration approach. The propagation losses are also higher. The propagation losses are related when the light signal passes through the material, how much light at the detection side we get. So there are some propagation losses which are mostly associated with the elements of third group of elements, and also limitation of mass production because they are not available as easily as compared to the silicon, and low index contracts as well. If we are able to come up with the photonic chips using the third group of semiconductor technology, there we can have various applications, like we can use them for the telecom, the datacom, sensing application, and biomedical application. If you just go through the what is latest happening in the photonic world, you'll find more and more devices are coming for the medical diagnostics and therapy issues. And most of them are based on photonics because photonic biosensors are proven to be very good for medical fields. So biomedical field is another interesting area whereby a photonics researchers can start working on it. Also, there is a possibility that we'll be coming up with the hybrid integration where we can use the multiple materials. See, the main issue with the photonic is in electronic industry, we can have all the components built by a single material. Either we can use the silicon or we can use the germanium. But here in the photonics, devices are heavily depend upon the material type. So some devices are built on silicon, some are built on INP or some other material. Even the lithium niobate is also proven to be good material to produce some of the photonic devices. So because of the unmatching of these material, we actually need a different kind of integration approach so that we can actually make them compatible with each other. There is a very interesting graph in between the INP-based integrated photonics and silicon-based integrated photonics. Here you can see the blue line, the blue dots, and the blue line is actually showing the growth of the slope, a slope which is showing the growth of the INP-based products, which started somewhere around 1985. And here you can see the many more products came into the picture with the help of the INP photonics. While 2005 onwards, we started with the silicon photonics. But the good thing with the silicon photonic is the slope is higher. That means in the coming time, it was expected that by 2030, the number of components produced by the silicon photonics would be more than the number of components produced by the INP photonics. Because you can see the slope is high. So it is going to sooner or later, it is going to catch the speed of the INP-based photonic circuits. I'll just skip few slides. There are very important major players which are already competing with each other to come up with the photonic integrated photonic based devices. One is the Infinera DTN. This Infinera, you might have heard about. It's a very good company which is producing a lot of photonic components. And indeed, this was the first company which introduced a first commercial product based on the integrated photonics. And you can see if you happen to be in data center or cloud computing centers or high performing computing centers, you'll see many more devices built by them. And most of the centers are using Infinera components inside them. Then Intel and IBM, they are also coming up with various photonic devices using the integrated approach. Some of the devices built by the Intel and IBM, they are not available commercially yet. They are using for their in-house application only. But sooner or later, they are going to come up with many more products with the use of integrated photonics. So what could be the next target, especially in integrated photonic circuits? We can get the laser on package using the third group of semiconductor. Since we are, as we saw, most of the people have started working with the silicon photonics. So we need to cope up with this problem that can we get the laser or the detector onto the silicon photonics also. So in that case, we'll have to come up with some hybrid solutions. To get the laser, waveguide, photodiodes, and other optical gubbins onto the processor die itself alongside the copper wires and transistors. So we can try to come up with the hybrid solutions of electronics and optical, like electro-optic components. by deploying silicon photonics technology for switch-to-switch interconnectivity at 100 gigabits per second. Similarly, development of PICs with the use of plasmonic, photonic crystal fibers, etc. And to tackle fabrication challenges, we would need to trade off between the power requirement, the cost, and the chip area coverage as well. If you see, the electronic chips are very small in nature, but the photonic chips are quite large. So we would need to have a trade-off in between the power requirement, the cost which we are putting into onto it to come up with the integrated photonics, and the chip area coverage. So we need a trade-off in between these three. If we see the market trend, why the silicon photonics is becoming popular, you can see the market trend is kept on increasing. Lot of money is being, lot of revenue is being generated by having an investment on silicon photonics. So by 2024, the more than $720 billion dollar is already generating a revenue through the silicon photonics. And here you can see this bar chart is actually divided into various colors. And these are showing the application area where we are using the PICs or PIC based product. Here you can see the most of the products are being produced for data centers and as well as the high performance computing, because we need our computing at a very faster speed, at a very faster rate. Like we have a AI, these days the AI field is very emerging technology. So in the AI, what we need to do, we need to do the data analysis, which is being from the various data which is being generated onto the by the devices. So there also in AI, the photonics can play a pivotal role to provide various products or various chips which will be enabling the AI techniques to compute the data or to analyze the data at a bit faster rate. Similarly, the concept is AI for photonics and photonics for AI. So this is the what the photonics can actually do for AI. And similarly, the artificial intelligence can also contribute to the field of photonics. Being an AI engineer, you can help us by identify the best material suitable for a particular product. Number one. The second is, since we are talking about the chips, we are going to place many components onto a dias. So you can tell me about the optimized solution using the AI, where I should place which device I should play at what, so that I can use it optimized way. And the third one is the AI techniques or AI algorithms can help us to evaluate the performance or photonic components, especially the sensors, because photonic sensors which are being used for medical treatments, they are coming up with the huge data, and we require the algorithms which can actually uh, analyze these data and provide us the best solution. So thereby we can apply the AI algorithms as well for to check the performance of the photonic chips. So this graph shows the global photonic integrated circuit market, which is estimated to reach at $3,554 million. So like which technology we are using, whether we are using the hybrid or the silicon photonics or only the simple INP photonics. There are few more graphs are available here, which are showing the components made, photonic components made by various material combination, which material having what kind of contribution they are producing, uh, putting to produce the photonic devices. Thank you very much from my side for this dedicated program.